So back in 1986, this guy actually managed to find a cure for a really complex blood disorder without ever setting foot in a lab.
Which is kind of the dream, right? No clinical trials, no test tubes.
Right, zero lab work.
Mm.
And he didn't invent some new chemical compound either. He literally did it just by reading.
Just connecting the dots.
Exactly. I mean, he systematically connected totally separate bodies of existing medical research that, just hadn't been read by the same people before. And by doing that, he found a completely new medical treatment just hiding in plain sight.
And that's exactly why we're doing this deep dive today. Because today, we are teaching AI to do that exact same thing.
But at a scale of, like, millions of documents a second.
Yeah, exactly. Which brings up the big question, what happens when AI stops just fetching facts for us and actually starts inventing science?
Okay, let's unpack this because this is fascinating. We've spent so much time recently talking about making AI better at executing instructions. Following the rules so it doesn't break things or just accurately summarizing a PDF.
Right, but execution was never really the end goal. It's just the precondition.
The table stakes.
Exactly. The ultimate frontier, the one we are crossing right now, is teaching systems to generate brand new knowledge. We are seeing the emergence of this so-called reasoning framework, and it's built on top of something called hybrid memory.
Which fundamentally shifts the AI from being this simple retrieval tool to an autonomous hypothesis generation engine. It's not about teaching an AI to survive a dinner rush at a restaurant. We're teaching it to invent a completely new dish.
I love that analogy. And fundamentally, most new discovery happens right at the very edge of known knowledge. So if we can represent all human knowledge in a structured system, an AI can use logic to actually extend that edge.
So for everyone listening, if you use standard AI chatbots for research or your own workflows right now, you definitely know the absolute frustration of asking a complex question and getting this highly confident, beautifully written, but completely wrong answer.
Oh yeah, the classic hallucination.
Right. You hit a wall where the system just can't actually think. So before an AI can invent new knowledge, it needs a perfect understanding of existing knowledge. And our sources today outline why standard vector databases, which are the engines powering basically all modern AI, why they just aren't enough for true discovery.
Yeah, to really grasp that limitation, we have to look under the hood at how different memory architectures actually function.
Okay, lay it out for us.
So vector memory, which is the default for most large language models right now, it relies entirely on cosine similarity in high-dimensional space.
Meaning it's probabilistic.
Right. It maps words and concepts into numbers, and it clusters them based on how often they appear in similar contexts. So it knows that, say, Paris and France are conceptually close.
But it only knows what things are like, not what they actually are.
Exactly. It operates on this fuzzy semantic recall. It's basically operating on vibes.
Which is, great for summarizing a long email chain, but it's terrible for rigorous logic.
Yeah, you wouldn't want to build a bridge with it.
Right. And then on the other end of the spectrum, you have lexical memory, which is the exact opposite.
Lexical memory knows exactly what was said. It's exact text matching.
Basically like running a Control-F search on a document.
Yes. It has zero semantic understanding, but perfect literal recall. The problem is, even if you combine those two, vector and lexical, you still can't really reason.
Because true reasoning requires graph memory. Let me try an analogy here to help visualize this.
Go for it.
Think of this hybrid memory like navigating a city. So vector memory gives you the vibe of a neighborhood. It tells you, hey, this street feels a lot like that street over in Brooklyn.
Which is helpful if you want to find a good coffee shop.
Right, but totally useless for actual step-by-step navigation. Then lexical search, that gives you a specific street address.
Okay.
But the graph memory, the graph is the actual paved road network. You can't navigate a city just on vibes. You need the physical, deterministic roads.
That analogy actually holds up perfectly at the mathematical level, too, because a vector store just cannot perform certain deterministic logical operations.
Like what? What's an example?
Take transitive closure, for example.
Transitive closure.
Yeah, it's this fundamental logical rule that says if A is located in B and B is located in C, then A is logically located in C.
Oh, right. Like if my keys are in my bag and my bag is in my car, my keys are in my car.
Exactly. But doing that requires a deterministic walk over a rigid road network. A vector store can't do that. It just sees three things that have a similar statistical vibe and sort of lumps them together.
It also can't detect structural contradictions, right? Like to a vector database, finding two different birth dates for the exact same historical figure It just sees two highly relevant, semantically similar facts.
Right. The vector space doesn't inherently understand the biological reality that a human being can only be born once.
Which is obviously a catastrophic failure point if you're trying to do actual science.
Oh, completely. True reasoning requires those deterministic, rigid roads. So in this hybrid memory architecture, the AI uses natural language processing to read documents and extract these subject-predicate-object nodes to build the graph.
So the hybrid memory becomes the substrate. It's the actual world.
Exactly, the physical reality of the data. And then the reasoning framework is the cognitive layer that sits on top of it, running symbolic logic to traverse those facts and derive new ones.
But, having a perfectly mapped road network doesn't actually put a car in motion.
No, it doesn't.
So if the AI has this massive, pristine graph of human knowledge, how does it actually decide where roads to drive down to find something new? Because having a map is very different from exploring one.
This is where we get into the operational mechanics of reasoning. To navigate this graph, the system uses a framework based on the work of Charles Sanders Peirce.
The 19th century American logician, right?
That's the one. He categorized human reasoning into 3 distinct modes. We often call it the DIA framework: deduction, induction, and abduction.
Okay, let's break those down. Deduction is probably the one we're all most familiar with. It's the realm of math and law. I sort of view deduction as the lawyer.
I like that, the lawyer.
Yeah, because it's strictly about proving what must be true based on the existing rules in the graph. Like, if the premises are true, the conclusion is absolutely airtight, it doesn't create new knowledge, it just polishes the gems we already own.
But there is a really fascinating irony here when you look at the literature on this. Large language models, even though they can pass the bar exam, are actually terrible at strict deduction.
Wait, really? They pass the bar but can't deduce?
Yeah, they struggle immensely with it, especially with counterfactual deduction or multi-step logic. Remember, LLMs are just probabilistic prediction engines.
Right, the vibes again.
Exactly. So when logic gets really complex, they tend to just guess the next plausible-sounding word rather than adhering to rigid rules. And that is why, in a true reasoning framework, deduction is deliberately not performed by the language model.
Well, that makes total sense. So the LLM translates the user's query, but the actual deduction is handed off to that deterministic symbolic engine we talked about.
Yes, the system acts as a neurosymbolic hybrid. As you said, the lawyer who proves the case should never be hallucinating the legal precedent.
Definitely not. Okay, so that's deduction. Next in the DIA framework, we have induction. This is the detective.
A detective, right.
Yeah, induction is noticing a pattern from a few specific instances and then proposing a general rule. So it's analyzing the graph, noticing that maybe a specific protein folds a certain way under heat in 3 different studies, and then proposing that this protein always folds that way under heat.
Right. It creates a probable rule from specific observations. And then finally, we arrive at abduction.
The doctor.
The doctor, yes. Abduction is looking at a set of symptoms, the end observations, and reasoning backward to propose the most plausible underlying cause.
So if you wake up, look out the window, and see a wet lawn, abduction tells you it likely rained overnight.
Exactly. It is less probable that the sprinklers ran at 3 a.m. and highly improbable that someone spilled a giant tank of water. You're working backward from the effect to the cause.
Okay, this is where it gets really interesting.
Yeah, Peirce made this profound observation about this specific mode of logic. He basically said that abduction is the only logical operation which introduces any new idea.
Because deduction just works the interior of our existing knowledge, right?
Yes. But induction and abduction, they go prospecting out at the boundary, they operate at the edge of the map.
But how does a piece of software actually identify an edge? Because for us, for a human, the edge of our knowledge feels like this foggy, abstract horizon. We sort of know what we don't know. But a computer needs a definable state.
Well, the edge isn't a fog to the AI. Because it has that graph memory, the edge is actually a structural shape in the data.
Structural shape?
Yeah, it's a mathematically detectable condition.
Okay, give me a concrete example of what that shape actually looks like.
Sure, so a structural shape could be a contradiction node. The graph might reveal that a single chemical compound is documented as having 2 mutually exclusive properties, just depending on which scientific discipline published the paper.
Oh, wow.
Yeah, so that contradiction is a physical shape in the graph whispering, hey, there is a missing variable here.
That's amazing.
And another shape is a cross-domain spark. This happens when a mechanism in one scientific domain structurally mirrors a mechanism in another domain, but they use completely different terminology.
Oh, so the AI detects the identical pattern and says, let's build a new road between these two neighborhoods that have never interacted before.
Exactly.
Which actually brings us right back to that story I mentioned at the very beginning of this deep dive. Because this whole idea of cross-domain discovery isn't just some modern AI hype. It was actually pioneered by a human.
Back in 1986.
Yes, by Don Swanson. He was an information scientist at the University of Chicago, and he developed this method called literature-based discovery, or LBD.
Right, because he hypothesized that undiscovered public knowledge actually already existed. It was just fragmented across different library shelves.
Yeah, because modern science is so intensely specialized, it creates these massive silos. Like, a biologist doesn't really read the literature produced by a materials scientist, even if they're fundamentally studying the exact same molecular behaviors.
They're speaking different languages in different buildings.
Exactly. So Swanson decided to test this theory by looking at a specific medical problem, Raynaud's syndrome.
A circulatory disorder.
Right, it causes restricted blood flow to your fingers and toes, usually triggered by cold temperatures or stress. And so Swanson systematically analyzed all the medical literature surrounding Raynaud's, and he extracted the core physiological nodes.
The symptoms.
Yeah. He found that patients with this condition consistently exhibited high blood viscosity, so thick blood and excessive platelet aggregation.
Okay, so those become the rigid, documented nodes of the disease state in his mental graph.
Exactly. And then Swanson physically left the Raynaud's literature. He completely changed gears and went to a totally separate silo of research, the literature on dietary fish oil and its active compounds, specifically EPA.
Completely unrelated at the time?
Totally unrelated. And as he read through this entirely different scientific domain, he extracted its nodes. And he found numerous studies proving that fish oil naturally reduces blood viscosity, decreases platelet aggregation, and limits vascular reactivity.
Which is just a perfect real-world execution of that transitive closure logic we were just talking about.
Yes.
Swanson basically built a graph in his mind. Node A, fish oil, acts on node B, thick blood. Node B is the direct cause of node C, Raynaud's syndrome. Therefore, A relates to C.
Meaning fish oil could potentially treat Raynaud's syndrome. And he made this monumental medical connection without ever running a single lab experiment himself.
He just bridged the gap between two disconnected graphs of human knowledge.
Yeah, and then independent medical researchers eventually conducted the clinical trials, and they completely validated his hypothesis.
Which is wild.
It is. Today, omega-3 fatty acids found in fish oil are just a standard, widely recognized natural therapy for improving blood flow and reducing those Raynaud's attacks.
The implications of that are staggering. I mean, it actually led Swanson and his colleague Neil Smallheiser to create the Aerosmith system.
Right, an early software tool for this.
Yeah, to help investigators manually find these hidden connections. But even with that tool, it was still a manual, painstakingly slow process.
I mean, it took Swanson months to find that one single connection, but now if you apply the reasoning framework we've been discussing to this exact methodology.
It changes everything.
Right. The AI doesn't have to read one paper at a time. It uses NLP to ingest millions of research papers, maps the nodes and edges into a massive hybrid memory graph, and then just deploys those DIA reasoning modes.
Deduction, induction, abduction.
Yes, and it walks thousands of connections simultaneously. It looks at biology, chemistry, physics, economics all at once. And when it finds one of those cross-domain sparks, it mathematically verifies the logic and actually writes its new hypothesis back into the system as it goes.
We are effectively talking about automating Don Swanson at a planetary scale.
But that raises a massive question for you and me and everyone listening. If an AI is essentially acting as this automated, scaled-up Don Swanson, pumping out thousands of highly plausible cross-referenced hypotheses every minute, what exactly is the human supposed to do?
Do we just retire?
Right, do we just step back and let the machine run science?
Well, actually, it's quite the opposite. The automation of hypothesis generation fundamentally elevates the role of the human.
How so?
So the philosopher of science Karl Popper argued that all scientific advancement relies on two distinct phases, conjecture and refutation.
Okay.
You make a bold, educated guess, that's the conjecture, and then you ruthlessly test it against reality to try and prove it wrong. That's the refutation.
So in this new paradigm, the AI takes over the conjecture phase entirely.
Completely. The AI becomes the ultimate tireless conjecture machine. But an AI doesn't live in the physical world.
Right.
It doesn't have a budget, it doesn't have physical lab equipment, and it certainly doesn't have a societal moral compass to
Yeah.
know which of its 10,000 hypotheses actually matter to human flourishing.
Ah, I see.
So as the supply of brilliant conjectures approaches infinity, the scarce resource is no longer generating ideas. The scarce resource is the human refutation.
It's choosing which ones to fund, running the physical lab experiments, and judging the real-world results.
Precisely.
And we are already seeing the leading edge of this shift in reality. I mean, DeepMind deployed a system called FunSearch that's actively finding new, verifiable solutions to open math problems.
Yes.
And there's another system, AlphaEvolve, that autonomously improved upon a core sorting algorithm from 1969 that humans hadn't been able to beat. And at Carnegie Mellon, they built Coscientist, an AI that independently designs and plans complex chemical experiments.
Those are the amazing success stories, yes. But we really have to look at the failures to understand the honest limitation, the real danger of this transition.
What kind of danger?
Well, consider a recent project called the AI Scientist, which was developed by the research lab Sakana AI. The goal was to build a system that could generate full, novel scientific papers end-to-end.
Wow. A completely automated researcher.
Exactly. But when independent researchers evaluated the output, they found critical flaws.
Like what?
The system was hallucinating numerical results to make its hypotheses look successful. It was citing outdated or completely irrelevant papers to support its claims.
Oh, no.
Yeah, the logic flowed beautifully, the formatting was pristine, but the actual scientific foundation was fundamentally compromised.
Wait, if the system can generate flawlessly formatted, highly convincing papers that are entirely wrong, we have a massive problem. I mean, we've talked about persuasion bombing in the context of social media, but this is persuasion bombing at the academic level.
Yes, it is.
If an AI is designed to generate hypotheses, and it uses perfect grammar and flawless rhetorical structure to confidently sell a totally flawed medical idea, how do we possibly defend against an AI that sounds that confident about a bad idea?
That is the defining vulnerability of using AI for discovery. Because the ultimate conjecture machine is, by default, the ultimate persuasion machine.
Right.
A language model is designed to sound authoritative, regardless of its accuracy. And this is exactly why a reasoning framework cannot be a black box where you just feed in a prompt and blindly trust the generated output.
So what's the defense mechanism?
The defense mechanism built into this architecture is what is known as the annotation table.
An annotation table. That sounds exactly like a bibliography.
Yeah.
But if the AI is already hallucinating the science, why wouldn't it just hallucinate the audit log, too?
Because the annotation table is not generated by the language model.
Oh.
Right? It is a deterministic output of the graph memory itself. It operates as a rigid, unchangeable audit log of the exact node edge traversal that led to the conclusion.
Oh, wow.
Yeah, so when the AI proposes that A treats C, the annotation table doesn't just give you a text summary, it provides the mathematical provenance. It shows you the exact source document for no A, the specific symbolic logic rule it applied, whether it was induction or abduction. And crucially, it flags any existing nodes in the graph that structurally contradict the new path.
So it actually forces the AI to show its math, line by line, completely outside of the language model's probabilistic text generation.
Exactly. And the discipline of the modern human expert is to audit this table, not to just read the summary.
You have to inspect the structural roots of the claim.
Yes. Researchers studying human-AI collaboration constantly warn against this phenomenon called falling asleep at the wheel. When a machine produces fluent, beautiful answers, human operators naturally lower their guard and just stop verifying.
We get lazy.
We do. The AI must drive the generation, but the human must retain the critical judgment. You don't verify the text, you verify the graph traversal.
Okay, so just mapping this all out for you listening. We started by realizing that getting AI to accurately execute instructions was merely building the foundation. The true goal is knowledge generation.
Right.
And we explored how building a substrate of facts using hybrid memory, moving past the probabilistic vibes of vector databases to the rigid, interconnected road network of graph memory, creates a landscape the AI can actually navigate.
Getting off the vibes and onto the roads.
Exactly. And we looked at how deterministic reasoning engines use deduction, induction, and abduction to push past the known borders of that graph.
Finding those structural contradictions and cross-domain sparks.
Finding the hidden connections, just like Don Swanson did with Raynaud and fish oil, but doing it across millions of documents simultaneously. And finally, we confronted the reality that this technology completely shifts your job. You are no longer required to be a data miner, endlessly searching for the needle in the haystack.
No, you become the chief adjudicator.
Right. Wielding the annotation table to protect against persuasion bombing, and deciding which of the machine's conjectures actually deserve to exist in the real world.
It fundamentally redefines the bottleneck of scientific progress. The bottleneck is no longer human imagination. It is human verification.
Which is honestly an incredibly empowering thought.
Yeah.
Because AI doesn't have a sense of self. It has no context for the physical world, and it has no skin in the game. It inherently cannot know which problems are worth solving to reduce human suffering or, advance our civilization.
Absolutely not.
And that limitation guarantees humans a permanent seat at the table. Judging the ideas, selecting the path forward, running the physical experiments, that is the most vital role in the entire process.
It really is. But I want to leave you with a final thought to mull over.
Okay, lay on us.
If we are entering an era where an AI reasoning system can perfectly cross-reference all human literature in seconds, if it can instantly generate robust new hypotheses by connecting domains that have never interacted before, what happens to our traditional concept of expertise?
Oh, wow. That completely flips the academic model on its head.
It does. When connecting the dots between molecular biology, quantum physics, and macroeconomics becomes as simple as traversing a database graph, where will the next massive breakthroughs come from?
That's a great question.
Will they come from the hyper-specialists, the researchers who have spent 30 years memorizing every single detail of one tiny subfield? Or will the next Don Swansons be the absolute generalists, the people who simply understand the architecture of logic and know how to ask the AI the right cross-domain questions?
The generalist suddenly has the tools to out-innovate the specialist. We started this deep dive talking about the difference between an AI surviving a dinner rush and an AI inventing a completely new dish. But the real shift is that the AI isn't the chef at all.
Yeah, right.
It is an infinitely fast, infinitely knowledgeable prep team processing every recipe ever written and handing us ingredients that have never been paired together in the history of the world. The AI preps the ingredients, but it's entirely up to us to decide what tastes good.
The kitchen is open.
Let's get cooking.